Hey folks, so I want to explain why cyclic groups or subgroups are abelian. So let G be a group and let A be an arbitrary element. The cyclic subgroup generated by A is all things of the form, well, the identity and then A combined with itself and then A combined with itself 3 times, etc. And similarly, A inverse combined with itself, A inverse combined with itself 3 times, etc. So cyclic subgroups are always abelian. And remember, a group is cyclic if it's just equal to one of its cyclic subgroups. So cyclic groups are also abelian. Let's prove this. So what does it mean to be abelian? It means that in your group, if you take two arbitrary elements, x and y, x times y is equal to y times x for all elements x and y in your group. So to prove that cyclic subgroups are abelian, so, let the cyclic subgroup generated by A be a cyclic subgroup. So to show abelian, we need to choose two arbitrary elements, x and y, and show that they commute, that x times y is equal to y times x. Don't call your elements x and y. We have better names for an arbitrary element of the cyclic subgroup generated by A. Call your elements a to the kth power or a to the mth power, where k and m are integers. So let a to the k and a to the m be arbitrary elements in this cyclic subgroup. So here, k and m are just integers. They could be 0, 1, 2, 3, or -1, -2, -3, etc. What do we need to show? We need to show that when I multiply them in one order, I get the same thing as if I multiply them in the other order. Okay, so I'm going to multiply them in both orders and see what I get. And then I'll conclude by saying, since these are the same, we've shown that this arbitrary cyclic subgroup is abelian. Right. So a good strategy is to give yourself the proper framework when you're trying to write a proof. The framework matters, in my opinion, more than the algebra does. Okay, so let's combine these. Let's expand these. Let's multiply these out. A to the k times a to the m, that's k copies of A. Let me give myself some more space. All right. So I combine A with itself k times. That's what A to the k is. And then I multiply this by A combined with itself m times. That's what A to the mth power is. What do I really have? I have A combined with itself k plus m times. And another name for that is a to the k plus m. When I combine a to the mth power and a to the kth power in the opposite order, I have a combined with itself m times. times A combined with itself k times. Okay. Really, I just have A combined with itself m plus k times. And another name for that is a to the power m plus k. But m and k are just integers, and we know that k plus m is equal to m plus k, just like 3 plus 4 is the same as 4 plus 3. So since these are the same, right, I could put this equality here. I've shown that these two arbitrary elements combined in this order is always equal to those two arbitrary elements in the cyclic subgroup in the opposite order. And therefore, cyclic subgroups are abelian. Thanks so much.